On the afternoon of March 23, 2019, nearly 48,000 tons of steel was battered by 60-knot winds and 8-meter waves off the coast of Norway. Inside the Viking Sky, 1,300 passengers and crew held on as the vessel suffered a catastrophic blackout and lost all power. Without propulsion or steering, the ocean takes over. The winds and waves pushed the massive cruise ship sideways at an average speed of 4 knots. Directly in its path, less than a ship's length away, was a jagged, lethal shoreline. A 100,000-ton vessel floats for the exact same reason a piece of wood floats. Buoyancy provides an upward force that keeps the object on the surface. But buoyancy offers zero resistance to lateral movement. It will not stop a ship from sliding helplessly wherever the wind and current push it. This vector schematic maps out force equilibrium. To stay in one place, a ship must achieve this state. Simply Newton's first law applied to fluid dynamics. Every environmental push from the wind and waves, represented by the red arrows, must be met by exact, perfectly equal green counter arrows pushing back. With the rocks approaching fast, the crew of the Viking Sky scrambled to drop both anchors in a final attempt to stop their slide. To know if throwing metal into the sea can actually halt 48,000 tons of moving steel, we have to look at the physics of how ships secure themselves against the ocean. The most controlled environment for a ship is alongside a dock. Here, the counterforce is provided by physical mooring lines tied to massive metal posts, essentially chaining the vessel to solid earth to counteract the ocean's pull. Securing a massive vessel requires a precise geometry of tension. Crews utilize a specific web called the 6 and 2 arrangement, locking the bow and stern with a multi-directional network of lines. Breast lines run at a near right angle from the ship to the pier, directly fighting lateral drift away from the dock. Meanwhile, spring lines run diagonally. They act as the ship's brakes, absorbing longitudinal force to prevent the vessel from surging forward and backward. Modern massive vessels rely on highly engineered synthetic materials, like high-modulus polyethylene. When the ocean pushes against the ship, these lines stretch under the immense load. They become massive, heavily tensioned rubber bands, storing up lethal amounts of potential energy. If the tension exceeds the braking load, the synthetic rope snaps and recoils at hundreds of kilometers per hour. Because the line weaves through various fairleads and winches, its trajectory is completely erratic. These unpredictable, deadly areas are known as snapback zones, where a single break can be instantly fatal to the crew. Even when tied directly to solid concrete, fighting the ocean with static, rigid tension carries extreme physical risks. Once a ship leaves the safety of the port and heads into the open water, engineers abandon static lines and turn to the mechanics of gravity. When a dock is unavailable, such as in the shallow coastal waters where the Viking Sky lost power, a ship must secure itself offshore by deploying an anchor. A common misconception is that an anchor pins a ship down through sheer weight. A modern stockless anchor weighs only a few tons, which is negligible compared to a massive vessel. Instead, its design relies on these pivoting, pointed arms, the flukes. They are engineered to dig deep into the seabed, but their only job is to lock the very end of the line in place. This cross-section reveals the true mechanism of offshore mooring. The actual counterforce comes from the line itself. Navigators pay out huge lengths of heavy steel chain. It is the sheer mass of this chain spanning the ocean floor that keeps the massive vessel in position. As the wind and waves push the ship backward, the heavy, sagging chain lifts slightly off the mud. It forms a catenary curve, functioning as a massive mechanical spring. Instead of snapping tight and ripping the anchor out of the seabed, the chain's weight gradually straightens out, smoothly absorbing the kinetic energy of the surge. This gravity-driven spring is highly effective in shallow coastal zones. However, if a ship needs to hold position thousands of meters above the seafloor, dropping an anchor weighing several tons and dragging a heavy steel chain across this environment isn't just risky, it is strictly forbidden. In ultra-deepwater oil fields, the seabed is often a dense patchwork of high-pressure pipelines and subsea manifolds. Because a dragging anchor could trigger a multi-billion-dollar environmental disaster, maritime authorities strictly prohibit physical mooring in these critical infrastructure zones. To remain stationary here, the offshore industry relies on dynamic positioning, or DP systems. A DP vessel drops no lines. It maintains absolute geographical position over the seabed by constantly adjusting its own propulsion. Maintaining position in the open sea requires napping movement across 6 distinct degrees of freedom. The system must continuously counteract forward and backward surge, lateral sway, vertical heave, horizontal yaw, forward pitch, and side-to-side roll. To execute this constant adjustment, the vessel is equipped with omnidirectional azimuth thrusters, capable of instantly directing thrust in a full 360 degrees. These are paired with highly sensitive anemometers to measure incoming wind and differential GPS units for centimeter-level spatial accuracy. This graph visualizes the math inside a common filter. Raw sensor data on a rocking ship is inherently noisy and lags behind real time. The system takes that messy sensor measurement, calculates the hydrodynamic models of the ship's specific hull, and combines them. It filters out the noise to calculate a single optimal estimate of the ship's true position, allowing it to instantly issue precise thrust commands. Deepwater positioning relies on continuous digital calculation rather than physical restraint. These algorithms allow a 100,000-ton vessel to hover over invisible coordinates, maintaining station even as the sea shifts around it. Yet, even with advanced mathematics, the ocean constantly hunts for weak points. In 2011, the production vessel Griffin Alpha was battered by hurricane-force winds in the North Sea. The immense physical strain exposed invisible metal fatigue in her anchoring chains. 4 heavy lines snapped, causing severe damage to the subsea infrastructure below. To prevent silent structural failures, the next generation of maritime engineering embeds microchips and optical sensors directly inside the steel links of the anchor chains. These internal nodes monitor tension and microscopic metal fatigue in real time, feeding live data into machine learning models. Engineers create a digital twin of the mooring array. The system predicts a failure days before a storm arrives, integrating mechanical strength with algorithmic prediction. Back on the jagged coast of Norway, the desperate crew of the rapidly drifting Viking Sky let their anchors loose. The heavy steel flukes plummeted into the dark water, successfully finding the mud of the seafloor. As the ship continued to surge toward the rocks, the hundreds of meters of chains stretched out behind the anchors. They formed a perfect catenary curve along the seabed. The sheer suspended weight of the steel lifted slightly, acting as a massive spring to smoothly absorb the ship's 48,000 tons of kinetic energy, halting it mere meters from a total disaster. The vessel had finally achieved force equilibrium. Whether relying on the mathematical precision of a Kalman filter to hover over a deep-water well, or the intense gravity of a steel chain to stop a slide toward the rocks, maritime survival always comes down to executing the exact physics of counterforce against an unforgiving ocean.